When a patient is diagnosed with ventricular tachycardia, a dangerously fast heart rhythm, and scarring on the heart tissue, the standard medical playbook is highly conservative. The protocol usually involves passive management, a strict regimen of beta blockers, and explicit instructions to avoid intense physical exertion. That was the reality for the subject of this dataset. For 4 years, every heartbeat was monitored by this exact piece of hardware, a Boston Scientific subcutaneous defibrillator implanted in the chest, designed to deliver a shock if the heart went out of rhythm. Instead of accepting passive management, he used his very diagnosis as the foundation for an active biomechanical experiment. The goal was to build a movement system that could functionally shield the heart from its own electrical triggers. We now have a 10-year raw dataset tracking that experiment. To see if the system actually holds up under extreme pressure, we are going to look at a side-by-side longitudinal comparison of his data from a period of high stress in May 2023 against an elite performance peak in May 2026. This specific 3-year window serves as the stress test. If the physical protocol is a fluke, the numbers will reflect the expected trajectory of aging and cardiac decay. If it operates as a consistent algorithm, the data will show systematic resilience. The hardware pillar relies on the 10-to-2 ArC, a specific geometric movement pattern. This diagram outlines strict rotational control zones. By pivoting within these windows, the subject eliminated joint shear and forced the core to stabilize the load. In 2023, the subject was 51 years old. He was 18 months post-defibrillator removal and was using no heart rate controlling medications while maintaining structural stability on the elliptical. By 2026, at 54 years old, executing the same 10-to-2 geometry, his mechanical output scaled to an elite cadence of 224 strides per minute. Despite the increase in speed, the logs show 0 electrical cardiac events and 0 joint degradation during the 2026 session. The durability of this framework suggests that even with a significant cardiac history, precise mechanical alignment can provide a stable environment for high-intensity work. This mechanical alignment is supported by the firmware, a specific method for programming the autonomic nervous system to process cardiovascular stress. During the 2023 baseline tests, a peak heart rate of 172 beats per minute was regulated by a strict 3-second inhale and 3-second exhale breathing pattern. This was intended to prevent the nervous system from defaulting to a panic response. By 2026, the intensity escalated to 13.8 METs and 266 watts of power. This pushed the engine to a peak heart rate of 180 beats per minute. This chart reveals a physiological outlier in the 2026 raw heartbeat intervals. Overlaid against the massive spike in physical output is a stable line representing an SDNN of 46 milliseconds, clinically categorizing the nervous system as relaxed. The nervous system remained balanced at its limit. This firmware programming documents a state where extreme physical output and neurological stress are functionally decoupled. The final pillar of the system is the fuel, or the internal metabolic environment required to support the physical and neurological load. The May 2023 data documents the system under duress. High psychological stress resulted in a stress score of 93, while energy dipped to a critical 7. Despite these crash markers, an anti-inflammatory nutrition protocol allowed him to maintain a high parasympathetic response during exhaustion. By 2026, the metabolic environment had stabilized. Through nutrient efficiency and a reduction in external stressors, the subject returned to a peak performance state. This metabolic control eliminates internal inflammation noise, which provides the foundation for the hardware and firmware to survive periods of intense trauma. The chronological reality of this dataset is that the subject aged 3 years between these two major tests. Standard biological expectations for a patient with this cardiac history would involve a measurable decline in performance metrics over a 3-year period. The 2026 performance metrics show a significant increase in capacity compared to the 2023 baseline, with higher cadence and more efficient recovery. This suggests the protocol functions as more than a fitness routine. It acts as a method for endogenous autonomic regulation. By aligning hardware, firmware, and fuel, this 3-year data window demonstrates how physiological stability can be maintained even in the presence of a